Okay, so today we're going to run through chapter 4 on your slides. All right. We're going to focus more on the end part of chapter 4 now, where we talk about limiting reactants and reaction stoichiometry. Okay, and this is called limiting reactant and the theoretical yield of a reaction. All right, so these are concepts you're going to hear all the time. All right, so we got to get very comfortable with them. Um, Basically, a limiting reactant is the thing in our chemical reaction that is going to run out before anything else does. All right, so if we go back to the example that we initially had where we were talking about making pizzas, we have this recipe. All right, now say that in my stocks, in my cupboards, in my fridge, it turns out that I have 4 crusts, 15 ounces of tomato sauce, and 10 cups of cheese available. Well, now how many pizza pies can I make? Right? For me to be able to figure this out, I have to know what is going to run out first. Because at that point where I run out of one of my ingredients, I can't make any more pizzas. And again, our chemical reactions are going to work the same way. Right? So what I'm going to do is I'm going to take each individual reactant. So in this case, it's my crusts, my cheese, and my sauce. And I'm going to use my balanced equation. And I'm going to figure out how many pieces I can make if I used up every single one of them. Right, so for the crusts, I know that I need 1 crust for every 1 pizza. So if I have 4 crusts, I can make 4 pizzas. For the cheese, I have 10 cups. I need 2 cups for every 1 pizza. So I can make 5 pizzas. How many pizza can I make using all 15 ounces of my sauce? Well, I need 5 ounces of sauce for every 1 pizza. So I can make 3 pizzas. All right, so I could make 4 pizzas with my crust, 5 pizzas with my cheese, 3 pizzas with my sauce. That tells me that after I'm done making 3 pizzas, I will not have enough tomato sauce left to make any more pizzas. Right? I'll still have some crust and some cheese left, which is delicious, but it's not going to make me a whole pizza, right? So this value here, this is the theoretical yield for my reaction. It's the amount of pizza I can make before I run out of one of my components, right? The reactant that produced my theoretical yield, in this case the tomato sauce, that's the limiting reactant of my reaction. Okay, it's what limits the amount of product I can make. It limits it because it runs out. All right, and these other 2 components, my cheese and my crust, these are my excess reactants because I still have leftover of both of them when I'm done trying to make my pizzas. Okay, so whichever of your reactants here gives you the smallest product value, that is your limiting reactant. Whatever the smallest product value is, that's your theoretical yield. Okay. So here's like a visual of what we're saying here. Your theoretical yield is going to be the least amount of product. Your limiting reactant is going to be the thing that produced the least amount of product. Okay. I'm giving you this in multiple forms so that you could, whichever way you can remember it, I want you to remember it, right? Our theoretical yield is based only on our limiting reactant. Okay, that's the only reactant where you can get the theoretical yield from. You cannot get a theoretical yield value from either of the other reactants that are present. Okay, those are basically, you know, you can't ever call 4 pizzas or 5 pizzas a theoretical value if you don't have enough soft to make those, right? And it works the same way in every reaction. Whatever your excess reactant is, it has nothing to do with your theoretical yield value. Okay. When we have multiple reactants, which we usually do, that limiting reactant, it's going to be completely used up before anything else. At that point, the reaction stops and no more product gets made. Okay? That's why that reactant is called the limiting reactant. Any reactant that is not completely consumed in a reaction, so the stuff that remains still, that's hanging out in solution, those are our excess reactants. Okay. Again, just a visualization to really reiterate the point that your limiting reactant and your theoretical yield, those things go together. Your excess reactant has nothing to do with your theoretical yield. The next important component is to look at what would actually happen in real life. In, if we're talking about chemical reactions, what would happen if you were in lab performing an experiment and trying to collect product? Okay, the amount of product that you end up with at the end of the day, that is called your actual yield, or your observed yield, or your experimental yield. Okay, and this number might be different from your theoretical yield, because theoretical yield, that's what would happen. That's how much product you could make if everything went perfectly. Okay, if nothing went wrong, you didn't lose anything, that's how much product you could make. So if we bring this back to real life again, assume that while making pizzas, okay, we drop one of them on the floor, and when we are done for the day, instead of having the 3 pizzas that we should have made, we only have 2. This amount here, these 2 pizzas, that represents our actual yield. It's the amount of product that we're actually walking away with. Okay, we can determine the efficiency of a chemical reaction by comparing the actual yield and the theoretical yield. And that comparison is called the percent yield. So if we take our actual yield and we divide it by our theoretical yield, multiply it by 100, what we're calculating here is called our percent yield. All right, and a very high percent yield means that we had a very efficient reaction. A low percent yield means it was extremely inefficient. Okay, let's talk about this last bit. Let's talk more about this excess reactant, because we're frequently going to have at least one, probably more than one, excess reactant in a reaction. And we need to know exactly how much we have left over. So let's go back to our nice simplified example here. If we want to know how much of each of the other components that we have left over, the first thing that we need to do, and star this little bold line here, because this step here seems to elude people. We need to see how much of each reactant we used up to make our product. Okay, and remember, in this case, our product is our theoretical yield, and that is 3 pizza pies. All right, so I need to know how many crusts did I use up to make 3 pizza pies. I have a 1-to-1 ratio, so I must have used 3 crusts up. Then I need to know how many cups of cheese did I use up making 3 pizza pies. My ratio of pizza to cheese is 1-to-2. So I use 6 cups of cheese. All right. Notice that this value here, the value that we start with when we are calculating our excess reactant, it is always going to be our theoretical yield. okay? It has to be our theoretical yield value. Once we calculate how much of the reactant that we used up, we can do some subtraction because we know how much we started with. We started with 4 crusts, for example. We know that we used 3 crusts up, so we must have 1 left over. The same is true for the cheese, the same process. I started with 10 cups. I used 6 cups up. I must have 4 cups left over. Okay, so let's take a look at this. Nitrogen dioxide reacts with water to form nitric acid and nitrogen monoxide according to the equation. Suppose that 5 moles of NO2 and 1 mole of H2O combine and react completely. How many moles of the reactant in excess are present after the reaction has completed? Okay, so we can set up a couple of simple conversions to look at this, all right? I can do it on my whiteboard for some clarity. Okay, so we want to know how much excess reactant remains after this reaction is completed. So to do that, we have to take 2 steps initially. And these are the same 2 steps that you're going to take for any limiting reactant theoretical yield problem. You always have to look at these starting amounts and then see how much product each one would make if you converted them all to that product. Now in this case, the question itself does not give us one of the products to look at, so you can pick either one. Sometimes a question will specifically say how much nitric acid was produced, or HNO3 was produced, or how much NO was produced. But in this case, it just said how much of your reactants are left over. That means you can choose either product to look at, okay? Your end result will be the same. So I'll just choose the HNO3 here. So I'm going to say, well, how many moles of HNO3 are produced if I have 5 moles of NO2, okay? So I'm going to look at my balanced equation and say, well, for every 3 moles of NO2, I'm going to make 2 moles of HNO3, okay? So 5 times 2 divided by 3, that's 3.33 moles of HNO3, okay? Next step, I'm going to do the same exact thing, but I'm going to do it for the H2O. Ooh, that's far too late. I like to do different colors so that we can keep the steps clear. So how many moles of HNO3 can I produce from 1 mole of H2O? Well, for every 1 mole of H2O, I can produce 2 moles of HNO3. Okay, so I can look here and say, well, that means that I can make, there we go. All right, now at this point, I know 2 things. 2 things. I know what my theoretical yield is, and I know what my limiting reactant is. Okay, I am going to cross out, you're going to look at these 2 values up here, okay? You're going to circle the smaller one. That smaller value here, this number, that's your theoretical yield. Okay, this number up here, you're going to cross it out because that number is garbage. And you do not need it. You will not need that number for any other part of your calculation. Okay? What this number tells you here, what your theoretical yield tells you, is that H2O, that's your limiting reactant. Okay. And now we need to figure out how much of our NO2 we have left in excess. Okay, so that is our next step. So to do this, we are going to first take this theoretical yield value and we are going to bring it over here. And we're going to rewrite it there because we always start this excess step with our theoretical yield value. Okay, so we are making 2 moles of HNO3. All right, now I have to figure out how much NO2 I used up to make this. So I'm going to look back at my balanced equation and say, well, for every 2 moles of HNO3, I needed 3 moles of NO2. That means that, cross that out, 3 moles of NO2 were used up to make the theoretical yield. Okay. This value of our used up NO2 is not our excess amount though. Okay. So now we know that we started out with 5 moles of our NO2. I'm going to erase this part up here because this is our last step in this part of the calculation. So we know we're going to do starting minus used up equals excess. Okay, so our starting amount was 5 moles. We used up 3 moles. That means we have 2 moles of NO2 in excess. Okay, so these are the steps for every theoretical yield problem where you need to find the theoretical yield, the limiting reactant, and how much excess reactant remains. Okay. Okay, so we come back here to our question, and it should be no surprise to us that the choice is 2 moles of NO2 are present after the reaction has completed. All right, so here is another summary slide, right? So our theoretical yield is the amount of product that can be made in a chemical reaction based on the amount of limiting reactant present. Our actual yield is the amount of product that is actually produced by a chemical reaction. And our percent yield is going to be calculated by taking the actual yield, dividing it by the theoretical yield, and multiplying it by 100. Okay, so now we're going to run through a visual example of each of these steps, kind of like we did with the pizza, but now with some chemicals here. So here is a balanced equation for the combustion of methane. Every 1 molecule of CH4 is going to react with 2 molecules of O2 to produce 1 molecule of CO2 and 2 molecules of water. Okay, so here is our question, here's our setup. I have 5 molecules of methane and I have 8 molecules of oxygen gas. Which is the limiting reactant? What is the theoretical yield? How much excess remains? So again, here you pick one of the products. Okay, I'm using CO2 for this example. If you did this entire question and you used H2O instead, you would still get the same result. Okay, and my first step in both cases is I'm going to take the amount of reactant I have and I'm going to see how much of my chosen product it forms. Notice that the products that I picked in both examples are the same product. Okay, you cannot use different products to compare. So once you pick CO2, you have to stick with CO2 for both reactants. If you picked H2O, you have to stick with H2O for both reactants. So I can see from my 1-to-1 ratio between methane and CO2 that if I have 5 molecules of methane, I'll produce 5 molecules of CO2. If I have 8 molecules of oxygen, I'm going to see that there's a 2-to-1 ratio between oxygen and CO2. That will leave me with 4 molecules of CO2. Okay, now again, at this point, you know the answers to your questions, right? You know that oxygen is the limiting reactant. Why is it the limiting reactant? Because my 2 product values, one was 4 molecules of CO2, one was 5 molecules of CO2. The smaller one is the important one. The smaller value is my theoretical yield. So remember that my theoretical yield is always going to be a product value. The reactant that produced the theoretical yield, that is my limiting reactant. Okay? What that means is that my methane must be in excess. And now I have to see how much of it remains. So I will take my theoretical yield value of 4 CO2 molecules, and I will start my calculation there. Then I'm going to look at my balanced equation to relate carbon dioxide back to methane, and it turns out that 4 methane molecules were used up. Once I know how many molecules were used up, I can do my subtraction. My starting amount minus the amount that I used up will give me the amount left over. I have 1 methane molecule left. All right, so now we're going to talk through another example. These are going to get bigger and bigger, obviously. So here we have the balanced reaction between NO plus H2 to produce NH3 and H2O. Okay, now we have these 2 starting values here. We have 86.3 grams of the nitrogen monoxide. We have 25.6 grams of the hydrogen gas. And we want to find the theoretical yield of ammonia in grams. So in this case, the problem is telling us exactly which product we are going to be focusing on, right? So we're going to figure out what the theoretical yield of ammonia is specifically, and then we are going to figure out how much of the excess reactant remains. And then at the end of the reaction, it tells us that we have managed to collect 44.4 grams of ammonia gas. From that, we're going to be able to calculate the percent yield. Okay? Now, at this point, I'd once again ask you to pause and see how much of this that you can calculate on your own, okay, before I talk through the rest of the example. We are going to start, of course, by converting each of our reactants into the particular product that I'm looking for. Okay, so in this case, we're focusing on the NH3. So I'm going to take 86.3 grams of nitrogen monoxide, use the periodic table to convert it from grams into moles. Next step, I'm going to look at my balanced chemical equation so I can convert from moles of nitrogen monoxide to moles of ammonia. Okay, so this would, if I used up all of my nitrogen monoxide, I would produce 2.8757 moles of ammonia. Right? Now I need to do the same thing for my hydrogen gas. I'll take my 25.6 grams of hydrogen gas, use the periodic table to convert it from grams into moles of hydrogen gas. And then I'm going to look at my balanced equation. Say for every 5 moles of hydrogen gas, I'll produce 2 moles of ammonia. Right? That means I would be able to produce 5.0794 moles of ammonia. Okay? So now I have to compare these 2 values. I compare these 2, and it's clear that this one's a smaller value. That value is my theoretical yield in moles. Okay? In moles. You can have a theoretical yield value in moles, and you can have a theoretical yield value in grams or in kilograms. So be mindful of the units that you're presented with. this is my theoretical yield value in moles. That means that this number right here, 5.0794, this value is garbage and you don't need it anymore. Okay. I'm also going to right away take this theoretical yield value that's in moles and I'm going to convert it into grams of ammonia. And I'll explain why once we get to the percent yield calculation part. But it's good to have your theoretical yield value in terms of both moles and grams, okay? Because you need both of those numbers. And you could just go back and forth between those two values using the molar mass from the periodic table. All right, so I need to know how much excess reactant remains, okay? I know already that my theoretical yield is 2.8757 moles of ammonia or 49 grams of ammonia. And I know that my limiting reactant was my nitrogen monoxide gas, right? I know that because it's the reactant that produced my theoretical yield. That means that I have hydrogen gas in excess. Now, to figure out how much hydrogen gas I have in excess, I need to know how much of it I used up to make my theoretical yield. Okay, so the first value that you write down over here is your theoretical yield value. I chose my gram value here, but if you had written down 2.8757 moles of NH3 here instead, that would be fine. You could skip this first calculation. Okay, but I started with 49 grams of ammonia. Now my first step, I'm going to use my periodic table to convert grams of ammonia into moles of ammonia. All right, once I have a mole value of ammonia, I'm going to look at my balanced equation and look at that 2:5 ratio between ammonia and hydrogen gas. Right, that will tell me how many moles of hydrogen gas that I used up. But my initial amount of hydrogen gas was given to me in terms of grams, so I'm going to now use the periodic table and convert moles of hydrogen gas into grams of hydrogen gas. And it turns out that I used up 14.49 grams of hydrogen gas. I know I started with 25.6 grams. I used 14.49 grams up. That means I have 11.11 grams of hydrogen gas remaining in excess. Oh, I did not do the last part of this. I'll do that on my whiteboard. We'll go back to the problem here. All right, let me just switch over to that. Okay, so to calculate your percent yield now, we're going to look at these two pieces of information in particular. So our problem tells us that at the end of our experiment, you've collected 44.4 grams. This value here, that's our actual yield. Okay, our theoretical yield is 49 grams. To calculate our percent yield, we're going to take our actual yield, divide it by our theoretical yield, and multiply it by 100. So that gives us 44.4 grams over 49.0 grams times 100. Let's see what that is. Like 90.6% yield. That's a very efficient experiment. Okay, here's another example. We obtain titanium metal from its oxide according to the following balanced equation. When 28.6 kilograms of carbon reacts with 88.2 kilograms of TiO2, 42.8 kilograms of titanium is produced. Find the limiting reactant, theoretical yield in kilograms, and the percent yield. How much excess reactant remains? Okay, so again, we have to look at the information that we're given. We're given 28.6 kilograms of carbon, so that is one of our reactants. It's reacting with 88.2 kilograms of TiO2. That's our other reactant. And 42.8 kilograms of titanium is produced. So that value is a product value. That means that this value here is our actual yield, and we will use this value to calculate our percent yield later on. But our first step here is going to be taking these two reactant values, our carbon and our TiO2, and seeing how much titanium each one can produce. So again, hit your pause button here and try to set this up for yourself. Okay, I'm going to look for the mole value for my titanium from each of the starting reactants. I'm using titanium specifically for this one because the question called for it. So step one is going to be converting from kilograms to grams. Once I have a value in grams, I will convert from grams of carbon into moles of carbon. Then I will look at my balanced equation, and I'm going to convert from moles of carbon to moles of titanium. Okay, and this would be the value of titanium that I could produce if I used up all of my carbon. Now I'm going to do the same set of steps for the TiO2. Kilograms to grams. Use my periodic table to convert from grams to moles. Use the balanced equation to convert from moles of TiO2 to moles of Ti. Okay, and this is the amount of titanium that I could produce from 88.02 kilograms of TiO2. So now I'm going to compare these values, and I can see right away which value is the smaller value. That value is my theoretical yield. My theoretical yield was produced from my limiting reactant. Okay, if TiO2 is my limiting reactant, then carbon has to be my excess reactant. So I can figure out a lot of information right after that first calculation. Now, my actual yield value was given to me in terms of kilograms. Okay, this means that to figure out my percent yield, I will need my theoretical yield to be in kilograms as well. So I'm going to take my theoretical yield value, all right, put it over here, and now I'm going to use my periodic table to convert from moles of titanium into grams, and then grams into kilograms. And I'm going to convert that mole value into a gram value for titanium. So now I have a theoretical yield of titanium in kilograms. Okay. What else did my question ask me for? Well, let's look at the percent yield since we have everything ready to calculate for it. My problem told me that I collected 42.8 kilograms of titanium. That's my actual yield. My theoretical yield was 52.9 kilograms of titanium. So my percent yield was 80.9%. Now to figure out how much excess I have, I'm going to need to know how many kilograms of carbon I used up to make 1.104 times 10 to the 3 moles of titanium. And remember, this value here, this is still my theoretical yield, but this is just my theoretical yield in moles instead of grams or instead of kilograms. I'm starting with the theoretical yield in moles here because it will require fewer calculations to convert it into carbon. Okay, so I can look now back at my balanced equation and see that I have a ratio of 1 mole of titanium to 2 moles of carbon in my balanced equation. And then I'll use my periodic table to convert moles of carbon into grams of carbon. Then my metric conversion to convert from grams into kilograms. So by producing 1.1043 times 10 to the 3rd moles of titanium, I used up 26.5 kilograms of carbon. To find the amount that I have left in excess, I'm going to subtract now. I started with 28.6 kilograms of carbon. I used up 26.5 kilograms of carbon, so I have 2.1 kilograms of carbon left.
Let's look at another example. Here we have an ammonia reaction, and we want to know the theoretical yield in kilograms. If we start with 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen, okay? We will also be calculating the kilograms of the excess reactant. Okay, so like all theoretical yield problems, our first step is going to be to take both of our reactants one at a time and calculate the amount of product we can form from the reactants if we use them up completely. Okay, that's always going to be our goal here. We have to see how much ammonia we can make if we use our hydrogen up completely, and how much ammonia we could make if we use our nitrogen up completely. We can't find the theoretical yield until we complete that process and we compare those two values. Okay, so let's start here. So we have 5.22 kilograms of hydrogen gas. And the first thing we want to do is to get rid of this metric prefix and convert our kilograms into grams. Okay. With that out of the way, now we can convert our grams of hydrogen into moles of hydrogen. And this step, we would use the periodic table to calculate this molar mass. Okay, so molar mass is used whenever we're going from grams to moles or moles to grams. Once we've converted this into moles of hydrogen gas, in the next step we need to move from hydrogen into ammonia. So we're switching substances. Whenever we switch substances, we're going to use the balanced equation coefficients to make that switch. Okay, so we look at our coefficients and we see that 3 moles of hydrogen gas are going to produce 2 moles of ammonia. Okay, and we can calculate the moles of ammonia we'll produce from this information. Okay, so pull out your calculator, try it out. Don't just wait for me to do the work. You should be trying it out yourself as well to make sure you're getting the same answer as me. Okay. Now we're going to do the same process, but for our nitrogen. Okay, so we start with 31.5 kilograms of nitrogen. Again, we're going to go from kilograms to grams. And because our periodic table is in the units of grams per mole. Okay, and then in this next step, we're going to convert from moles of nitrogen into moles of ammonia. And we see from our balanced equation that there's 1 mole of nitrogen for every 2 moles of ammonia. Okay. Okay, so if we use up all the hydrogen, we can produce 1726 moles or 1726 moles of ammonia. If we use up all the nitrogen gas, we can produce 2248 moles of ammonia. All right, so between these two values, the smaller value is the theoretical yield, and this value is garbage, and we're never going to use it again. Let's cross it out so we don't get confused. Okay, so 1726 moles of ammonia is our theoretical yield. right? And our theoretical yield value is the value that we are going to use to find out how much of our excess reactant is left. Which reactant is our excess reactant? Well, we've already decided that our theoretical yield was 1,726 moles of ammonia. The reactant that produced our theoretical yield is hydrogen. Hydrogen must be our limiting reactant. Okay, so let's keep track of this up here. Limiting reactant is hydrogen, and our theoretical yield is 1726 moles. Okay, that means our excess reactant is nitrogen. To figure out how much nitrogen is left over, we need to know how much we used up to produce our theoretical yield. Okay, so we have to start that calculation by writing down our theoretical yield of ammonia. And then we have to figure out how much nitrogen we used to make this amount of ammonia. So we're going to backtrack through our calculation. We go back to our balanced equation and see that 2 moles of ammonia will produce 1 mole of nitrogen gas. In 1 mole of nitrogen gas, there are 28.02 grams. And I'm going to go one step further and convert this into kilograms because my initial mass of nitrogen gas is in kilograms, and I would like my units to match so I can do my subtraction. Okay, so let's do that calculation. And I get 24.2 kilograms of nitrogen gas was used up. All right, so I know how much nitrogen I started with. I know how much nitrogen was used up. So to find out how much nitrogen was left over, I'm going to subtract those two values. Okay. Now we have a theoretical yield value right now that's in terms of moles. Okay, and that's fine. You may be asked to report your theoretical yield value in terms of moles or in terms of grams. All right, so just be prepared for that. If we wanted to report this theoretical yield value in terms of grams, we would just simply have to use the molar mass of ammonia to calculate that value. Okay, we can do that calculation right here. So we have 1726 moles of ammonia. And 1 mole of ammonia, we have okay. It's going to be a very big number, so I'm going to convert it into kilograms so it's more similar to the numbers that we started with. But again, the problem didn't specify the units of your theoretical yield. Oh no, it did. It said, what is it? All right, so we're doing the right thing. 1726 times 17.034 divided by 1,000. Okay, so our theoretical yield in terms of kilograms will be 29.4. All right, let's look at one more. Okay, we'll try this one out as well. We're starting with 167 grams of Fe2O3 and 85.8 grams of carbon monoxide, and this is going to produce 72.3 grams of iron. Okay, and this question runs the full gamut. We're going to find everything, everything about this reaction. Okay, so let's start our first step. We are going to use each reactant and see how much iron that the reactant can produce if it's fully consumed. That's always the first step of any theoretical yield problem. Okay, so we have 167 grams of Fe2O3. I'm going to use the molar mass. Okay, and then in our next step, we're going to compare the moles of Fe2O3 to the moles of iron. And I'm focusing on iron because this is the value that the problem gave an actual yield for. And now we're going to repeat that process for the carbon monoxide. Okay, and then according to our balanced equation, we have a 3-to-2 ratio here. So 3 moles of CO will produce, sorry, just CO, will produce 2 moles of Fe. Okay, so when we compare these two values, we see that this is the smaller of the two values. So this number will be our theoretical yield in moles. That means that carbon monoxide is our limiting reactant. Okay, and that means that we'll have some Fe2O3 in excess. So why don't we find that excess amount first? So we'll take our theoretical yield value. Remember, the larger number is garbage. So we'll take our theoretical yield value, and we're going to see how much Fe2O3 we used up to make our 2.04 moles of Fe. Okay, we're going to use our balanced equation ratio to convert from moles of Fe to moles of Fe2O3. And then we'll go into grams. Okay, and again, this step tells us how much of our reactant we used up to make our theoretical yield. Okay, so we used up 162.9 grams of Fe during this process. So to find out how much we have left over, we're going to subtract the amount we started with, our 167 grams. Oh, sorry, that's Fe2O3. And we're going to subtract the 162.9 grams from that. And we have 4.1 grams of Fe2O3 left over in excess. Okay, that's all. When they say in excess, they mean the amount that's left over. Right, now the last part of the problem asks us to calculate the percent yield, rather. And to do that, we're going to need to first convert our theoretical yield value into a mass value. Okay, and that's because when the problem provided us the actual yield is in terms of grams. And these two units have to match for us to calculate a percent yield. So I'm going to take my 2.04 moles of Fe, and I'm going to find the mass of that. Okay, so this is my theoretical yield in grams. Okay, this was my theoretical yield in moles. Okay, both are correct expressions of the theoretical yield. One's in grams, one's in moles. Now to find my percent yields, I'm going to take my actual yield, which is the amount I really made during my experiment. So that's 72.3 grams. I'm going to divide it by my theoretical yield. And I'm going to multiply it by 100. And I get a percent yield of 63.5%. Okay. That is the remainder of the theoretical yield limiting reactant problems for the chapter. The last few slides of the chapter just revisits combustion. So be sure to remind yourself again what the properties of combustion are. We've talked about it a lot. We talked about it in chapter 3 when we're doing actual combustion analysis, but we also talked about combustion a few different times during the course already, right? Whenever we have oxygen kind of combining with one of our carbon-based compounds over some kind of flame, right? That's going to be like our definition of combustion. That's what we'll think about in terms of combustion right now. Our combustion reactions are going to produce carbon dioxide, or if there's no carbon in the reaction, it can produce some other kind of oxide. And our combustion reactions will produce water or water vapor. Okay. Our combustion reactions are always going to emit heat. That will be one of the products as well. And one of our most common examples of a combustion reaction is going to be natural gas with oxygen, right? You should be able to, at this point, look at a description like this and be able to provide the balanced equation for this type of combustion reaction. Okay, so they want you to write a balanced equation for the combustion of liquid methanol. And if we think about combustion just in terms, I mean, the most basic terms that we're talking about here, which is we're combining a substance with oxygen over a flame, and we're seeing what results. So let's take that knowledge and we'll try to apply it to the methanol that they're talking about in this equation. They gave us the formula for it. Okay. We know that our combustion means we're going to be combining it with oxygen. Okay. And the products are going to be some kind of oxide. We have carbon in our product, so it's going to be our carbon dioxide. And it's going to be water. right? So this goes back to balancing, because this is our skeletal reaction here. So now we want to go through the steps and just balance this reaction to make sure that we have a balanced combustion reaction. And we're only going to have carbon, hydrogen, oxygen present in on both sides of this reaction. Okay, so we're going to go through and balance. I've got 4 hydrogens over here. I've got 2 hydrogens over here. I'm going to just start by doing this. Okay, so I got 1, 2, 3, 4, 3. So let's go through. We want to change this. We don't like this odd number of oxygens here. So I'm going to put a 2 in front of my methanol. Like we've discussed before, some of the balancing is a little trial and error, but when you do change something, there should be like a reason behind it. So I don't want to have an odd number of oxygens, so I'm going to put this coefficient of 2 in front of my methanol to even out this oxygen value on this side. Even if it changes everything else, I can fix that and worry about it later. So now I have 2 carbons. I have 1, 2, 3, 4 times 2 is 8 hydrogens. And I have 1, 2, 3, 4 oxygens. All right, so I have to go back over here and fix what I kind of messed up over here now, because I need 2 of these carbon dioxides. And 1, 2 times 2 is 4, 5, 6. And I have to fix my hydrogens. So instead of 2, I'm going to have a 4 in front of my H2O. 4. And that's going to become 8. Okay, so I've got 2 oxygens that are coming from my methanol. I need 8 oxygens total. So I must have 3 O2 molecules. This will provide 6 oxygens. If I add it to the 2 oxygens that I get from my methanol, that'll give me a total of 8 oxygens here. And then I'm all balanced. Okay. Your combustion reactions that you're going to be asked to identify at this point are not going to be any more difficult than this, though. Okay, so as long as you're comfortable with writing out the skeleton reaction and balancing this type of combustion, then you know what you need to know at this point.